Back, everyone. We're going to get started. Today we're going to keep talking about binary trees. Since we've been doing such a good job, we're already halfway through this week's content. Wow. I'm just going to do a lightning review of the stuff that we were supposed to talk about today, but talked about on Friday because we were fast. To delete a node from a binary search tree, there are three sort of different cases you need to consider. The easiest case is if a node has no children, so it's just a leaf node. In that case, you just set its parent's child field, left or right, depending on where it is on the tree. You just set that field to null. Simple as that. If the node has one child, the delete operation gets slightly more complicated, but not that much more complicated. All we have to do is swap the node with its child and then delete the old node. So in this case, we're deleting node 2. It has one child, 3. So we put 3 in 2's place and then take away the 2. Still pretty easy, as the name implies. Another example from the slides, we want to delete 15. Its only child is 17, so 17 takes its place, 16 moves up with it, 15 is gone. And keep in mind, if you're programming this, you would have to update all applicable pointers. So if your nodes have a pointer to their parents, which is a very good idea for operations like delete, you'll have to update that too. Still pretty easy. Now let's get tricky. Say we want to delete the value 27 from the binary search tree. This node has a left child and a right child, so it's not immediately clear what we're supposed to do. We're probably going to end up promoting one of its descendants, but which one? There are multiple algorithms for this, but the one we're going to use in this class involves finding the successor of the node that we're deleting. This is another thing from what should have been earlier this week, but was actually last week. The successor of the node is the one that would immediately follow it if you were printing out the nodes in order. So the next node. You could also think of it as the node with the smallest value that is still greater than the current node. No matter how you think of it, the successor to 27 in this tree is 32. This gives us a pretty neat property that we could take advantage of. You might have thought earlier on, maybe we could just replace the node with one of its children. But, of course, the node's children can also have 2 children themselves. Say we wanted to replace 27 with 36. That would preserve the binary tree's search property, but you'd still have this extra child to deal with. You'd be back to square one, basically. The successor, on the other hand, might have a right child, but it will never, ever, ever have a left child. So think about why that is. the successor is the smallest value that is greater than the current value. If the successor had a left child, say we had the value, 31. I'm going to draw that. So say the successor actually did have a left child. Because of the binary search tree property, this left child would be less than 32 and greater than 27. And since it's less than 32, that 31 node that we just added, that's the new successor to 27. In general, the successor will never have a left child because if it did have a left child, that would be a better successor to the node we care about. Because the successor has no left child, it immediately follows that it has at most one child, which isn't highlighted yet, but very soon we'll be able to take advantage of that fact. The two easy cases of binary search tree deletion happened when the node we wanted to delete had no children or just one child. So using the fact that the successor only has one child, we're going to be able to sort of reduce the problem to one of the easier cases. But before we do that, we swap the node to be deleted with its successor. This breaks the search property. The tree shown on this slide specifically is not a binary tree. You could tell because 27 is not greater than 32. But we'll fix that very soon. How do we fix that, you ask? We delete it. Since the successor was guaranteed to have at most one child, once we swap the node we want to delete into the place of the successor, like that, now the node we want to delete will have at most one child. And this was the reduction I was talking about. Reduction is like a cool math term for turning one problem into an easier problem, so you have an easier time solving the original problem. You'll see a ton of those if you go into more theoretical comp sci courses. So yeah, we just did a reduction from the tricky case to the two earlier cases. In this case, deleting 27 uses the much easier case. It has no children, so boom, gone. We just delete it. Like I mentioned earlier, there are other deletion algorithms that are possible. But the one I just went over is like the canonical one we'll use in this course. If you know about a different deletion algorithm and then you use it on a quiz or the exam or something, you probably still get full marks because the result will be correct, but the marker will be confused and perhaps angry, so just stick with this algorithm. And to summarize, kind of repeat what I said earlier this class, the delete operation has three cases. If it has, or based on whether the node you want to delete has 0, 1, or 2 children. If it has 0 children, you can just delete it. Nothing depends on it. So you don't have to make any other changes after you delete it. If the node you're trying to delete has one child node, you can just promote that one child node to take the parent's place and then delete the parent. excuse me, if the node to be deleted has 2 children, then there's not an obvious way to promote one of the children while maintaining the binary search tree property. So you swap it with its successor, and then that turns the delete operation into one of the easier cases. Now we'll do a more long-winded example. We're going to delete some values from a tree. If you're studying for a quiz or the final, or you just want some practice, there are definitely some binary tree creators or visualizers available online. So try starting off with a tree like this. Attempt to delete stuff, not just the ones that are in these slides, and then use whatever tool you found to verify that you did it correctly. In this case, we have the slides to verify our work. Oh wait, this is going to be kind of a mess if I try and draw stuff, is it? Huh. Too bad I can't erase from a PDF. I'll just do a bunch of scrolling. The first node we're going to delete is 25. Oh, and of course, as always, I encourage you to work along, even work ahead if you're really good. And then that'll hopefully help you really get it. But if you don't feel like doing that, just watching is fine. We want to delete 25. 25 has 1 child. That is 21. So we're in the still pretty easy case. 21 is going to be promoted to where 25 once was. And that's it. Ta-da! 36 is a bit trickier. It has 2 child nodes, so we need to look for its successor. Luckily, finding said successor is pretty easy. The leftmost node of its right subtree is the root of its right subtree. You can eyeball this. The smallest value that is greater than 36 in the binary tree is 39. So we're going to swap 36 and 39, and then I guess I could draw that X in either place, and both can be a kind of correct interpretation. Pretend that 36 is here. Boom, boom. And then 39 will be up there, and 40 will be here. Okay, 18 is pretty gnarly because while it is in the same case as when we wanted to delete 36, it has 2 child nodes. The matter of finding its successor is going to be a bit more complicated, but not that much more complicated. Our trusty successor finding algorithm will still work. Go to the right, and then keep going to the left. The successor is 20. As I keep saying, the smallest value that is larger than the one we care about, 18. So we're going to put 20 here and 18 here, and then delete 18. This reduces to the very easy case because it won't have any children anymore. So we can just delete it. Last part of the example was to delete 20. If we were doing all these examples separately, deleting 20 would have been the easy case because it's a leaf node. It has just one successor. I mean, just one successor. It has 0 children. But having deleted 18, that ended up restructuring the tree a bit in order to preserve the binary search tree property. And now 20 has 2 child nodes. That aside, it's the exact same as the previous example. Its successor is 21. We swap 20 and 21 and delete 20, which is now easy to delete because it has no children anymore. Ta-da! Something like this might be on the quiz. Now we're going to move on to a slightly different topic, a tree traversal. This is actually a more general graph theory concept, just being able to visit all of the nodes and list them in some order. But we're going to talk about them for binary trees first, because the nature of trees, that is not having any cycles or loops, makes it a lot easier to think about traversals. Like, what's the correct order of nodes for a graph that looks like this? It's a bit weird. Let's just stick with trees. And usually, it's worth mentioning, usually the purpose of a tree traversal is to perform some operation on each node. Most obviously, printing. You just want to output what is in the binary tree. But you could imagine other operations doing this too. I don't know, maybe you want to compute the average value in your binary tree. You would have to do this traversal in order to add up all the values and also count them and then divide them by the count. You know how it is. There are 3 forms of traversal, pre-order, post-order, and in-order, which might remind you of arithmetic expression parsing and might be foreshadowing for assignment 4. Maybe. Actually, have barely started making it. But I'm thinking of doing a question about arithmetic expression parsing because turns out binary search trees are a really neat way to store arithmetic expressions. But we're getting ahead of ourselves. In a pre-order traversal, we act on the current node first and then consider its children. So basically you do whatever operation you want to do on the current node. So print it, add it to a total for the sake of computing an average, something like that. And then you do a pre-order traversal on its left child, its left subtree, rather. They're technically equivalent, but it's better to think of them as subtrees in this case. And then a pre-order traversal on the right subtree. We call it a pre-order traversal because the current node is acted on first. You should hopefully be able to take a pretty educated guess on what post-order and in-order do, because this is actually a pretty nice naming convention. But just hold that thought in your head for now. So we're going to do an example by doing a pre-order traversal on the above tree. Consider our trusty pseudocode. Pre-order involves doing something with the current node and then doing that thing with the left subtree and then the right. A big reason behind my spiel from earlier about how traversals are just easier to think about with trees as opposed to general graphs is that it gives you an unambiguous choice for what the first node of the tree should be. Whenever we traverse a tree, we always start at the root. So I'm going to number these nodes in the order that they're operated on. 18 is number 1 because we did it first. After we act on 18, according to the code, we're going to then do a pre-order traversal on the left subtree. So starting at 12. We do this second. I guess from the perspective of node 12, it is first, but we're talking about the order that the values are printed, overall. Now for the second step of our pre-order traversal of the tree starting at 12, we do a pre-order traversal of its left subtree, which is rooted at 6. And then, the recursive stack should be building up in your head right now because, oops, I forgot how to count. The earlier pre-order traversals are still happening. The ones starting from 18, we're still in the middle of that pre-order call on the left subtree, and eventually that's going to finish and we'll do a pre-order traversal on its right subtree, eventually. But for now, we do a pre-order traversal on 6's left subtree, here. And then we finally have a recursive call that gets past that left subtree call. I suppose with this exact pseudocode, the next step would be to throw a null reference exception because 2 doesn't have a left subtree. Oh, what are we going to do here? This is pseudocode. It's for communicating a concept much more than it's for actually running correctly. You could just pretend that there's a decent null check before these 3 lines of code. So now that we've kind of sort of done a traversal of the left subtree of node 2, now we go to the right. Nothing on the left, nothing to the right. We finally finish our recursive call. So we all know and love recursion. The recursive call for node 3 will pop off the call stack. And then the same will happen for 2 because we just finished traversing the right subtree. On 6, from its perspective, we just finished traversing its left subtree, and we need to traverse its right subtree. Like that. I'm going to go a bit faster now because I hope the concept of going down the tree and then going back up the tree through the recursive calls should be a bit clear right now. And this will be more nicely illustrated on the next slide, spoiler alert. But the nature of the pre-order traversal gives us a pretty nice structure or order to how we traverse the tree. Try and figure out what it is before I finish talking about this slide. So we just finished traversing the left subtree of node 12. We traverse the right. No left, traverse right. Traverse left. No right. Return, return, return. Return to the root. That's crazy. Then we'll go all the way down that right left subtree. Return, return, return. Go to the right. Check out the left. Dead end. Finish off by covering the rightmost nodes in the tree. Bada bing, bada boom. Of course, I only did that so that I could talk along with the traversal. A much better visual representation of the traversal is right here. And I think this is pretty neat. It wasn't at all obvious from the source code. Act, pre-order, don't know what that'll do. Wasn't at all obvious, but the sort of emergent property of this is that a pre-order traversal will go all the way down one side of the tree before returning and repeating the same process. And since recursion is so cool, that means it always traverses the entire left subtree of a given tree first. And gradually moves from left to right. You'll notice that the order of values printed is dumb. It's not sorted at all. Don't worry, that'll be covered in another traversal. But in many cases in graph theory and usage of trees, it's useful to go all the way down a given path before trying a different one. Now remember what I talked about earlier with how, based on the fact that a pre-order traversal had the action on the current node before the recursive calls, you could probably figure out what the post-order and in-order traversals look like. And as was hopefully predictable, post-order does the action on the current node after the recursive calls. So let's see what the post-order traversal looks like. I guess we're going to have to hold some stuff in our head for now. Because when we start on 18, we're not going to actually do the thing yet. We do its recursive call first, traverse its left subtree. Likewise, at 12, we're going to traverse its left subtree before doing anything. Traverse that left subtree too. Attempt to traverse the left subtree of 2, but that doesn't exist. So the next thing to do is traverse the right subtree. And since 3 has no children, both of its recursive calls terminate immediately. And then we finally act on it. I'm going to go even faster through this one because as far as I can remember, this is kind of completely useless. I'm sure I'm forgetting something, but I don't think this has any sort of practical application unless you want to do like a depth first search and then print stuff in reverse of the search order. In the real world /assignments, you're probably going to be doing pre-order and in-order traversals most often. So we're done with this subtree. We return to the root. And remember that we still have to do the post-order traversal of the right subtree before acting on the root. So we do that. Recurse, recurse, recurse. And then just keep returning from the recursive calls and doing whatever operation you're doing on the nodes. Did I miss one? Oh no, 17 nodes. Like I said, not immediately useful. I shouldn't say that there are no applications of this. There's probably like some super abstract mathematical thing for which post-order traversal is really useful. And then, as is the case with most math stuff that seems to be useless, whatever weird, advanced, abstract thing uses post-order traversal, theoretically, will turn out to have extremely important applications in quantum mechanics or something 20 years after it's discovered. That's just sort of how math works, it seems. But let's do something that is immediately applicable, the in-order traversal. Like you can hopefully predict, this one has the action on the current node in between the two recursive calls. We operate on the left subtree, then operate on the root, and then operate on the right subtree. So let's see what that looks like. Sort of like the previous traversal that we did, we have to just keep in our heads the path of recursive calls we're taking, because we start at the root but don't actually do anything with it until after we've operated on its subtrees. So we remember that we started at 18, go to the left subtree, remember that we started at 12, go to the left, remember that we started at 6, go to the left, and then, since the algorithm was to traverse the left, do the current, traverse the right, node 2 doesn't have a left child, so its recursive call to the left returns immediately, and we actually act on it. Then we recurse to the right. 3 is next. That has no children, so we return. We're done with 2, so we return. Now at 6, we've traversed its left subtree. Now we're going to operate on it before going to the right. Boom. And then to the right as promised. Like that. We continue in that general sort of order. Notice the sort of weaving around that we're doing. Nodes being adjacent in the tree doesn't necessarily imply that they'll be next to each other in the order that we're creating. Instead, the ordering has a much more useful property that you should look out for while I'm doing this drawing. And then I'll just point out what the property is after I'm done. In any case, we're done with the entire left side of the tree. We operate on the root and do the same thing with the right subtree. Recursion is so fun.
8, what isn't supposed to be 9?
Oh, true. I was totally looking at 7. Thanks. So we go to the right, recurse all the way to the left. Return our way up that tree. Do the same thing on the right. We're doing a similar sort of weaving through as we did here. The right child isn't immediately printed because it has a left child, but the rest is straightforward. So, do you think that there's anything interesting or perhaps meaningful about the order in which we visited the nodes? Turns out, this is how you traverse the nodes of a binary search tree in order. In this case, ascending order. The first ones to be used are the smallest ones, and then each one is larger than the last. It's nice. And I think you can do a traversal in descending order by reversing the order of the recursive calls. Act on the right subtree before acting on the left. Either way, it's cool and fun. We have this data structure that looks kind of abstract, and it wasn't immediately clear how you would traverse them in order. Might remind you of the hash table that has no way of traversing its items in order. But through clever use of recursion, we were able to do exactly that. New topic. The height of a tree is the number of edges on the longest path from the root to a leaf. We're going to count edges in this course. Some sources will count nodes instead of edges, but it doesn't really matter. The height of this tree is 3 because the longest path from the root to a leaf is right here. Alternatively, there's another longest path right here. In both cases, it's 1 edge, 2 edges, and then 3 edges. Cool. If you were to count nodes instead of edges, you would end up with a height of 4. A devious source of off by 1 errors. So in this class, make sure you're counting edges, and whenever else you're using binary search trees, make sure you're counting whatever your boss tells you to count. And if you're the boss, just make sure that you choose one and stick with it. And I think this little note about asymptotic notation is pretty neat. Remember that constant multiples don't change anything in asymptotic notation, and any constant amount of anything is considered big O of 1. In this case, 3 and 4 are both constants. They're just one off of each other. So for this specific tree, they're both big O of 1. We're going to find a formula for the height of a tree in general, and we'll find that for that, it doesn't matter for that either, whether you're counting nodes or edges. But all the stuff about consistency I said earlier applies if you want the exact count of the height. New thing to think about, we let h be the height of the tree and n be the number of nodes in the tree. This is sort of the convention that is commonly used. Now, in terms of the height, what's the worst case time complexity of the insert, search, and delete operations? As always, try to work it along, try to work ahead if possible. And then the delete operation has another wrinkle to consider. What if the delete function receives a pointer to the node to be deleted? So you don't have to search for this node. Like if I wanted you to delete 36, what if I gave you a reference to that object instead of saying just delete 36? I don't know where it is, find it. You're the computer. Does that change the complexity of the delete operation? Intuitively, it should. But let's think about those operations. I think I'm going to scroll up and find one of the more complicated trees in a form that doesn't have these annotations. Yeah, this one's good enough as an example. So let's think about the insert operation first. What are the conditions that'll make it so the insert operation takes as many steps as possible? Well, remember that the insert operation uses the search operation. It looks for where the node containing the value you want to insert should be, and then places it there. If we want to, I'll talk about the best case first. The insert operation, and thus search, terminates as quickly as possible if, actually wait, we're only talking about insert for now. Search works kind of differently, even though insert uses search. The insert operation terminates as quickly as possible when the thing that you want to insert is as close to the root as possible. In this case, an input that would produce the best case would be something between 21 and 27. Like say I wanted to put in 25. That would go right here. I only had to go through one edge before reaching the node that will turn out to be the parent of the thing I want to insert. Conversely, this should get the gears turning on what the worst case for insert is. Since best case was as close to the root as possible, worst case will be as far from the root as possible. Something like 4. In this case, the algorithm would have to traverse 1, 2, 3, 4 edges before finding the thing that it has to traverse, or before finding the place to put the node that you want to insert. And that's the worst thing that can ever happen. uh, inserting a node doesn't involve going up the tree ever. It only goes down the tree. So the worst case for it is down the tree, meaning as many edges as possible. So we see that in the worst case, the insert operation will have to traverse h edges, as many edges as there are in the longest path from the root to a leaf. So we say that the worst case time complexity of the insert operation is big O of h. We don't know exactly how many operations it's going to take, but we know that it's going to grow. It's going to be proportional to h. The cost function for this algorithm would probably have an h somewhere, not raised to an exponent. Now let's talk about search quickly, and then I think I'll leave the very last bit of this slide deck for tomorrow, and then perhaps go another week ahead. I promise I won't go too crazy on how far ahead we get. Nothing I say is legally binding, but I think if we go more than 1 week ahead, like if we're suddenly going on slides for that are supposed to be from 2 weeks from now, I'll just cancel a class or two, give y'all a break. But anyway, the search operation follows very similar ideas. In the best case, it'll terminate as quickly as possible. Starting at the root, it will take as few steps as possible before finding what it's looking for. In this case, you get the best case if you're searching for the root. Now, for worst case, you might think that maybe it's going to be if we're searching for, 3, 16, something like that. But it's actually slightly more nefarious than that. The worst case for the search operation is if you're looking for a node that doesn't exist, but if it did, would be on a very long path from the root. Same as those insert cases, actually. If we searched for the value 4, we would go all the way from the root of the tree to the farthest ones away from the root. And then we'd fail, just return that this node doesn't exist. As such, the time complexity for the search operation in the worst case is also O of h, because the worst case complexity, or the worst case for this algorithm, involves doing some operation h times. Cool. That's it for today. See y'all on Wednesday.